Arun, you can start.
Okay, sir. So, everybody is welcome to UL Space Club webinar session 51. We just completed our 50 sessions of UL Space Club webinar series. And now we are moving on to the 51st session of our webinar series. We started our webinar series during the pandemic conditions of COVID-19 issues. At that time, our programs were stuck due to the pandemic regulations for offline activities like space camps. So we started thinking about what are the new activities that we can do. At that time, the team of UL Space Club came up with an idea to conduct a webinar series. We just started a webinar series with a plan to conduct only few sessions to interact with the experts to study more in the area of space and STEM. But later we realized that the students in the circle of UL Space Club has a great enthusiasm towards this particular topic of space and STEM. And we continued the webinar series, and now we are on the 51st session of our webinar series. Once again, very happy to welcome all of you to UL Space Club webinar series. In this 51st session, we have an interesting topic like interdisciplinary research in physics and biology. That it will be handled by an expert speaker, and the speaker will be introduced by our Shahil sir. Before going to Shahil sir, I have few instructions for the participants who are attending this webinar. You can use the chat window for your questions. You can type your questions in the chat window while a speaker is having his presentation. At that time, you can type your questions in the chat window, and our team, UL Space Club team, will select your questions for the question and answer session. You will get an opportunity to directly interact with our expert, and you can ask the question at that time. Please avoid unnecessary messages in the chat window. And we request everyone to switch off your mic and camera throughout the meeting unless you are asked to switch on it. You can switch on it when you are asked to ask the question directly to the speaker. At that time, you can switch on your mic and camera. Otherwise, please switch off it. it will be an interruption. If you switch on it, it will be an interruption to other participants when they are listening to the speaker. So please don't try to do that, and please don't try to share your screen. As you know, there will be a share your screen button in Google Meet, but don't try to do that. It will be an interruption for other participants when they are listening to our speaker's presentation. So please don't try to share your screen. That are the general instructions that we have, and we will have a quiz competition for all participants who are attending this webinar session, and the quiz competition will be conducted at last of the webinar session. At the ending time of webinar session, we will provide a Google Form link which will have the quiz questions, and the fast and accurate answers will be provided with a prize from your Space Club. So that about the quiz, and we request everyone to support us for our next programs also. Especially, we have already announced a program related to the Foundation Day and World Space Week celebrations of your Space Club. It will be conducted during 4 to 10 of October 2022. So we request support from everyone. And once again, I welcome everyone, all the new participants who have just joined the webinar. So let's move on to Shahi sir, and let's hear about the speaker, and we can have a wonderful session with our expert from Tata Institute of Fundamental Research. Shahi sir, over to you.
Thank you, Varun. We have been sitting here for the past 2 years, more than 2 years. We have started this session 23rd of May 2020. The COVID pandemic came to this world, and we all were stuck there. But the students initiated this process, and we are continuing the monthly webinar series. And a lot of students are participating in these things, and a lot of students are utilizing these talks as we are streamed through our UL Space Club webinar series is already there. And the US Space Club that established at Calicut under the guidance of E.K. Kuti, former director, ISRO. And we started this work continuously for the past 6 years, and we are getting enough support from the public community and this scientific supporting system from dual CCS here. And today we are in the 51st webinar series sitting here. The topic here is the interdisciplinary research at the interface of physics and biology. Now the whole world is speaking about the interdisciplinary approach rather than sticking on a particular subject. So that's a great idea. That's today the whole world is accepting, because the nature itself is the interdisciplinary manner. Everything is coded in the nature. People are in search of the secret of the things there in support of various branches of science. And today we have a great speaker from a great institution of India, Tata Institute of Fundamental Research, TIFR. It's Bangalore campus. There is another institute, there is National Center for Biological Sciences. And we have a great speaker and great scientist of India. We are proud to have him in this occasion. Dr. Shahi Thutupalli. He is currently works as Siemens Center for Study in Living Machines at National Center for Biological Sciences, TIFR, in Bangalore. And he also holds a joint faculty position in the International Center for Theoretical Science, TIFR. In 2011, he obtained his PhD in physics for his work in active matter at the Max Planck Institute of Dynamics and Self-Organization in Germany. He then moved to Princeton University for a postdoctoral fellowship. Since 2015, Shahi has been running a curiosity-driven research program in India on topics related to physics of living systems. A specific focus of research is to understand how the physical organization of biological systems affects the functioning and vice versa. Now, when we say an organism is living because of the movements or the physiological things happening there, and the physics and biology is closely related with the subject of chemistry, and TFR is conducting several researches in chemistry, biology, physics, mathematics, and computer science. And there is integration of all these branches of science brings the greatest novel knowledge about the science system all over the world, and we are contributing a lot of scientists, and they are encouraging a lot of students all over India. It's a great institution, and US Space Club is so glad to be in contact with these great institution and a great scientist from TIFR and NCBS. So I welcome on behalf of US Space Club Dr. Shahi to our forum, and I welcome all the veteran scientists or the students, teachers, and the common people who are gathered here, who are watching through this Google Meet, and those who are watching through the YouTube channel, and welcome all of you once again, and welcome our chief guest to present his wonderful, enthusiastic presentation for our students. Welcome, sir.
Thank you so much, Mr. Shajal, for this extremely kind introduction. And somewhat embarrassed by the kindness of your introduction. Thank you so much for that. And thank you also to Varun for introducing the session, and of course to Kutti Uncle, as I would call him, for giving me this opportunity to tell you a little bit about the kind of work we do, etc. So I'm going to share my screen and get started. And please let me know if everything is working okay. So I hope you can see my slides.
Yes, please.
Yes.
Visible. Oh.
Okay, thank you so much. Thank you. Okay, so as you heard, I am a faculty member at the so-called Simon Center for the Study of Living Machines, which sits within the National Center for Biological Sciences in Bangalore. I will tell you a little bit about this towards the end, but at the outset, you might already be wondering why someone like me who studied physics is sitting in a biology center. And in some ways, I've given away some of that with the title of my talk, that the research that we do is interdisciplinary, and that it sits at the interface of physics and biology. But what I will probably want to convey in my talk is that really biology, physics, and all these various other subjects are our creations. Nature really doesn't care. And our effort really is to understand the world for what it is. So let's dive right in. And I'm sure this is not something new for many of you, that the universe as we know it extends many scales, all the way from the very, very small to the entire universe itself. And, somewhere along the scale come what we recognize as biological objects, such as the cell or a human, and so on. What we also probably know is that these various scales would typically, in our way of studies and in our textbooks, etc., be organized into these hierarchy of sciences. Normally, one would hear that there is a basal or a fundamental way in which to think about all of this, which could either be, let's say, philosophy or logic or mathematics and so on. There are specific subjects like physics or chemistry which relate to matter. There's biology which relates to life, and so on and so forth, right? And not only do we have this view of the hierarchy of sciences in our head, but very often in the way we interact, in the way we study, in the way our institutes are organized, etc., there is also a notion in some ways that some fields are not only more fundamental, but also purer or higher or deeper, whatever you want to call it, than others. There is this sort of joking cartoon, some of you may have seen it, that the psychologist will look at the sociologist and say, what you're doing is just applied psychology. And the biologist will say, hey, but psychology is just applied biology. And ultimately so on. And the physicist will say, okay, you know what? it doesn't matter. All of what you're doing is just physics. And then ultimately the mathematician might say, hey, look, none of all this is true. We are the most fundamental guys. But what I want to convey to you is I think that this is a very wrong view of looking at the world. That there is really no such hierarchy. But more importantly, I don't think there is even a hierarchy of sciences as it is presented in this slide itself. Right? This is a picture that I took off the internet. This is really not my picture. But what I want to tell you is that there is really no hierarchy over here. Yeah? And as Mr. Shajil already said, nature does not care for the labels of physics or biology or chemistry or whatever else. Right? Nature just operates. For example, effort comes, in a very deep way when one tries to study biology because of these various different aspects that come together in one system. And therefore, it might behoove us to just drop disciplines and not care, but rather understand nature at its own terms rather than on our terms of physics, biology, or chemistry. So with that said, I want to slowly, I'm going to try and go slowly in this talk, build up what it means to understand, what it means for us to look at the world, so on and so forth. Okay. So this very question that I asked, what does it even mean to understand this universe, right? It's clearly spanning many scales. There are subatomic scales, there are atomic scales. There's the entire universe itself. There's biology somewhere in between. What does it even mean to understand this stuff? And each of us, of course, will have a different view of what it means to understand. But today I'm going to present one particular view of what it means to understand. Right? See, for example, for a doctor, to understand biology might mean to be able to cure a disease. Whereas for a physicist, it might mean something else. Whereas for a sociologist, it might mean something else. Right? So I'm going to present to you today one view of what it means to understand. And to present this view, I will take a simple example. And that is of the phases of matter. And I'm sure all of you know from daily experience, there is this video I hope you're able to see that's playing below. It is a video of an ice cube which is being heated. Right? And this is not a surprise for you at all. But the ice cube is a solid. And as you start heating it, it melts. It becomes water. Water is a liquid. And then if you heat it further, the water starts to boil. And then it becomes a gas. Right? And so there are these what we call phases of matter, solids, liquids, and gases. And as you also know, this is not unique only to water. Right? You also can have nitrogen, which forms a liquid. It of course forms a gas. You can have dry ice, which is carbon. Carbon is a solid. It can become a liquid. It can also become a gas. So this phenomenon that we are seeing here, solids, liquids, and gases, is a fairly universal phenomenon in the world around us. So what does it mean to understand these phases of matter? What I'm going to try and tell you is that can we understand how a liquid forms because of the interactions that exist between the units of this material? Let's take water as an example. What I mean by a unit is one single molecule of water, right? So when we are heating this water, we are not changing anything about the material, right? We are only increasing temperature. The molecule of water is the same, whether it is at minus 30 degrees or whether it's at 100 degrees or whether it's at 40 degrees, the molecule of it is the same. But still, think about the collection of the water molecules has changed, right? So in this way of thinking, let's say there's one of these units, one of these black circles is the water molecule. That itself has not changed when you've changed the temperature. What has changed really is the interaction between these units or interaction between these molecules. And it is those interactions which have somehow encoded for this collection of water molecules to be a gas or a liquid or a solid. So what is the example of such an interaction between units? Again, another daily example is that of gravity that we all know. If we jump, we're going to fall. And that is because our body, our mass, interacts with the mass of the Earth via this interaction, which we call gravity. Right? Another way of saying it is that we experience a gravitational force. Right? And therefore, these two particles, let's say us and the Earth, do something when we are separated in distance. Right? So if we are separated in distance, there is a force that attacks us as a function of distance and as a function of our masses. So that's one example of an interaction between units. So what about the interaction between water molecules? Let's say it's a much more complicated one than this simple gravitational interaction. Why? Because there are electrostatic interactions, there are weak chemical bonds, there are all kinds of possible interactions between these units that ultimately give rise to the entire material itself. Right? One way of depicting these kinds of complicated interactions between atoms or molecules is the so-called Leonard-Jones interaction, or the Leonard-Jones force, or the Leonard-Jones potential. Just like a gravitational force, gravitational potential, this Leonard-Jones potential could describe the interaction between some two very small-scale units, such as atoms or molecules. What is the nature of this Leonard-Jones potential? First, let's go back to this gravitational potential. So this gravitational potential, this force of gravity, as some of you may know from your textbook, power of 12 and distance to the power of 6, unlike distance to the power of 2 in the case of gravity. So if I plot this function f as a function of this distance, it is going to look like this red curve over here. Okay? So there is a maximum for this function, and then it goes to 0 very far away, because as you can imagine, as the distance keeps on increasing, because the distance appears in the denominator, this force, the term itself, becomes smaller and smaller and smaller. Right? So it goes to 0 eventually. And there is a maximum somewhere. What this means really is that, let's say there are two objects over here below a certain distance, which is that, let's say they start to touch each other. When they start to touch each other, they repel each other very strongly. When they're far away, they attract each other. And so there is a sweet spot that they occupy, which is the peak of this red function. Right? And so these two molecules like to sit at that distance from each other. And therefore, this distance is the distance at which these molecules would like to find themselves. So let's say they are molecules of water. There will be many, many, many molecules. Each one of these molecules is force, and eventually they will all arrange themselves in an optimal distance from each other. Okay. But then what distinguishes the fact that this arrangement is a solid or a liquid or a gas? So if you remember my picture that I drew over here, and you may also know this one. Okay. So you may remember from this picture that in a solid, the atoms or the molecules are arranged in an orderly fashion, like in a crystal. Right? They have a fixed distance between them and so on. Whereas in a gas, the other extreme, they are completely disordered. These molecules are very far away from each other and so on. And in a liquid, it's somewhere in between. The distance is somewhat intermediate, but also there is no real order like in a solid. But what I told you was that these units or these atoms or molecules are just all interacting with each other via this force, which means if I put a bunch of them together, they must eventually settle into some equilibrium distance with respect to each other. What affects that? What affects that, as we all know, is temperature. Right? Because what temperature means is that these atoms and molecules are not staying still. They're constantly moving. The higher the temperature, the faster they're moving, etc. So in some ways, there is a competition between temperature, which is trying to make everything move away from each other, and this interaction force, which is trying to keep everything together. Right? So there is a balance between these two forces that eventually dictates how the molecules will themselves behave. So if I try to, so the temperature will also be like an energy. And if I try to draw this energy on this same scale as this Leonard Jones energy, if the temperature is so high that the energy, the thermal energy, makes the system sit very high up, it'll be a gas. Right? But if the temperature is cold enough and all the molecules and atoms are able to come to this peak or this minimum position, then it forms a solid, and somewhere in between there will be a liquid. Why did I give you this very complicated example and very complicated discussion over here? The point of all this discussion for me was to tell you about what it means to understand a phase of matter, right? I have brought to you the concept of this interaction force. I have brought to you this concept of temperature. I have brought to you this concept of a competition between these two. And I have also told you that as you change this competition, material or matter organizes itself into different states without us having to do anything in order to organize it. Right? So this is one view of saying, oh, I understand states of matter. Understanding the relationship between temperature and this. You see over here that there are some numbers, that's 2.7, 24, and so on and so forth. So these numbers might change, whether it's water or any other material, but the functional form itself may not change, right? So this is another level of understanding that you can have, which is that I have said that the picture I have drawn over here for you in terms of organization of states of matter does not rely on the specifics of the material itself, but rather on some general considerations. Right? So uncovering such general considerations is another form of understanding. For example, Newton's law of gravity that we saw earlier, this M1 and M2, it doesn't care whether it's an apple and earth, or whether it's earth and the sun, or whether it is two other masses. The functional form remains the same, right? So that's another way or another description of us understanding the universe or the world. That is to draw this sort of general picture that we can describe. Ultimately, an output of science could be a diagram like this. What is the phase diagram? It corresponds to the transition between gases and liquids. Okay? So what you're seeing here on the y-axis is temperature. On the x-axis is density. Okay, what does it mean, density? So you see over here in these three pictures of gas, liquid, and solid, there are more number of molecules for the solid than there are for gas. Right? In other words, the density of molecules for the solid is more than that for the gas. We also know from our daily experience that this is at a higher temperature than this. Right? Therefore, you can imagine that there would be two parameters. One is the temperature itself that you can change. The other is you can also change the density to affect this behavior. In our daily experience, we can only change temperature because that's what we tune on the hot plate, right? But let's say I'm also able to go inside with some magic hands and able to pull out molecules and change the density. Then also I can affect this transition from solid to gas. That is what is captured in this picture of a phase diagram, right? So there will be temperature and there is density. So when the temperature is sufficiently low or the density is sufficiently low, which is this curve, and in the region within this curve, all these materials behave like liquids. And anything above this temperature or above this density, they behave like gases. And what you're seeing here, and we know from everyday experience that the boiling temperature of water is different from the boiling temperature of an oil or the boiling temperature of a gas, etc., right? But what you're seeing over here is the data that's being plotted for neon, argon, various different materials. And you're seeing here that all the data is falling on top of each other on the same curve, right? And this phase diagram is telling you that irrespective of this material and irrespective of the exact value of this temperature, I can form a coherent picture of materials and the transition between gases and solids. See, this is another level of understanding, right, that I'm trying to draw your attention to. One is understanding in terms of interactions. The other is understanding in terms of materials. This third one is understanding in some terms of some general underlying principle, which is universal across all these materials and gases and liquids and so on. Now I want to take you to a slightly different level of thinking. Now we said, okay, let's say we have water and we change the temperature and so on. We go to these different states of matter. But let's say I were to pose the question to you, what state of matter is sand? What about sand? Is sand a liquid or is sand a solid? And so on. Okay. There are multiple ways of answering this question again. So again, let's look at this picture of the scales of universe. And you look at the scales of the universe and ask, what is sand made of? Sand is ultimately made of atoms, right? It's made of silica, it's made of aluminum, oxygen, carbon, etc., etc. It's made of all of those things. When all of those things come together, the atoms come together, they will form some molecules, and the molecules will form crystals, and the crystals form, let's say, a grain of sand. Okay? So you might say, hey, the grain of sand is a crystal, and therefore sand is a solid. Now, what if I pick up a whole bunch of sand in my hand? What kind of material is that? An individual of grain is, of course, solid because it's a crystal. But what about a fistful of sand? Is that a solid? Is that a liquid? What kind of material is that? Because again, from daily experience, we know that if we have sand in an hourglass, it flows. It flows like a liquid, right? But we also know that artists are able to take sand on the beach and make solid-like sculptures with sand. So here's a very complicated material, which ultimately is made of atoms only, right? And those atoms come together to form a small unit, which is the grain of sand, which is a solid. But when you take many of those grains of sand together in a fist, it exhibits a completely different kind of behavior. Right? In some cases, it looks like a liquid because it flows. And in some other cases, it looks like a solid because it can be sculpted, like stone. So this is a very complex problem, it turns out. To answer this question of whether a sand is a solid or a liquid is not a very easy problem. Another example of this kind of material is toothpaste. Right? Sitting in the tube, the toothpaste behaves like a solid because it just sits there, right? It doesn't flow. Right? But the moment you squeeze on it, it flows out onto your toothbrush. So it's another strange material which behaves like a solid and a liquid, depending on the context. So a physicist might say, hey, look, I understand, like we understand phases of matter. I understand a grain of sand. It is a solid. But suddenly, for the physicist, the understanding breaks down when you ask, what about the fistful of sand? We really don't know the answer to that. And so here is a very thought-provoking cartoon that was drawn recently by this guy called Munro, where he says areas of physics by difficulty. In school, some of you in high school may not yet have learned, but soon you will learn Newton's laws. You might have heard of relativity, quantum mechanics, and so on. And you might think, oh, wow, these are really hard subjects. But it turns out the simple understanding of sand is much harder than any of these things because we don't even know how to classify it, whether it's a solid or a liquid, and so on. If some of you are interested, there is this very beautiful article in the New York Times written from where I've also taken that cartoon about what makes sand soft. Soft is another way of saying we really don't know whether it's a solid or a liquid, it's just a soft material. Okay? So I want to now take this one step further. In this example, we started with atoms, molecules, they organized into a crystal, but when we took many of them, they already formed something which is very complicated to understand. And what can be harder, let's say, than understanding the physics or understanding sand? I would think things like viruses, bacteria, humans, societies, these are much, much harder to understand than these things because, as I will tell you, these are all aggregates of atoms and molecules in very special ways. But you might be saying, hey, wait a minute. You started with some very simple examples of physics, and now you are going into the axis of biology. This is biology, this is not physics. Right? And of course it's harder to understand. You're just telling the obvious, and you're just using the gimmick of words. But what I told you earlier is nature does not care, right? Nature really does not care. This biology, chemistry are labels that we have put. Nature is just operating. And ultimately, if you look at biology, I can also think about it from the atom level upwards, right? So just like we asked about sand, what is sand and so on, let us ask what is biology made of? Again, ultimately, at some level, biology is made of atoms, right? It's and subatomic particles eventually, right? So it's made of, instead of silicon, it's made of carbon, nitrogen, phosphor, etc. And we all know that these atoms come together to form molecules, and those molecules organize to form cells organize to form organs or tissues, and these tissues will organize to form animals or plants and so on. And all of those things come together to form an ecosystem. Okay? But unlike this sand, so you already start to see the parallels I'm drawing over here. There are many levels of organization, both in our everyday life, everyday material, as well as, of course, in biology. And what I've tried to tell you over here is that just because we understand, and this level that we are of a single grain of sand, which is a crystal, we understand very well. Physics understands that level very well. But just because we understand that very well does not mean that we can take many of those grains of sand and predict the behavior of sand. Right? From the atomic level, I cannot tell you at all whether if I take 1 million particles of sand, whether they will flow or whether they will sit together in a sculpture. Okay? But biology is that plus so much more. Right? I cannot tell you at all, well, I take all these molecules and put them together to form these molecules in cells, and that will form an organ and so on. It is not at all obvious that that collection of things can do all the various functions that biology does. Sand simply flows, or you can sculpt it and so on, but biology does way, way more things, right? A single cell, what you're watching is a single cell of bacteria which is growing and dividing. Here is a video of cells of bacteria which are swimming. Here is a video of a cell, and what you're watching in green and red are various molecules which are moving inside the cell. Here is a video where one of our immune cells is chasing after a bacterium. Right? So the sensing and dynamic response, chasing after the bacterium, and it is eating it. Here is a video of a cell killing itself. Right? So spontaneously committing suicide. And here is a grand video of a whole collection of bacteria which are evolving antibiotic resistance almost in real time. Right? So what you're watching over here is a gradient of antibiotic, 0 antibiotic, level 1 antibiotic, level 10 antibiotics, and so on. And there is a bacteria which is growing on top of this plate, and you will see that the bacteria is spreading and evolving resistance to this antibiotic, this arrow over here, this antibiotic resistant bacteria, and so on. The point I want to make here is that even though all of these things are simply collections of atoms and molecules, they are able to perform these incredibly complex and diverse set of behaviors. Right? Just like the sand is also a collection of atoms and molecules, but a bunch of sand is able to exhibit very interesting features. Biology does even more remarkable things. Right? I'm going to show you a video over here. This is an embryo, an egg of a salamander, and you will see this salamander developing. That's the initial egg. And you see that it was initially a single cell, and that single cell has become 2, it has become 4, it has become 8. And there is some structure over here that has formed. That structure is flowing. You can see that there is a rearrangement of these molecules, and eventually some shape is emerging. And there's a tossing and turning of all these cells. There are some cells, as you can see in this video, that are rapidly migrating or moving inside that embryo. Presumably a heart has formed now, right? There's a beating of a heart. And what is happening is that there is more development. And eventually you're starting to see some form coming up over here, like an embryo of fish, a salamander here. And eventually this thing breaks out and gets out, right? What I want to point out to you was that when this entire video started, right over here, let's say, oops, I'm getting sorry. At this very initial stage, it was nothing more than a soup of molecules, right? It was a soup of molecules. And those soup of molecules are somehow, so you will, if I didn't tell you this was biology, let's say an alien came onto Earth, you will see this. This alien, I don't know the gender, if it's he or she or not. This alien will see this. They will see something flowing. It will look like a liquid. But then they will also see that it looks like a solid because there is a structure, a shape to this thing, right? But that shape is also moving, and so on and so forth. So then, how am I supposed to understand this, right? What does it mean to understand biology now? Should I ask questions like, is biology or this, is it a solid? Is it a liquid? Are those the correct questions? Or are the correct questions, is this a machine? Is this a computer? How can I understand that? Are those the relevant questions? We don't know yet, right? I mean, it is all of these questions in some ways and answering all of this that means to understand biology. Okay? And unlike the solids, liquids, and gases that we discussed earlier, if we zoom in to a cell and ask what is the structure of a cell, just like we ask what is the structure of a solid or the structure of a liquid, let's ask ourselves the question, what is the structure of a cell in the same way, right? So here I'm showing you pictures from this fantastic book called The Missionary of Life by David Kutzel. He's a scientist, but also an artist. And so what you're watching here is a painting of a bacterial cell that he has made. But what is special about this painting is that this is not from imagination, right? This painting depicts our actual images from actual cells, right? And this is a true-to-life painting, so to speak. I'll come into a little bit more detail of that later, but let's discuss the overall structure. And this will not be new to many of you. This is a biological cell, of course. There is a membrane around it. This membrane is comprised of a certain kind of molecule. Then if I look inside, there are other molecules called proteins and sugars and so on and so forth. This huge thing in yellow is the DNA. Right? Now let's look at a zoomed in version of this thing in the red box. So here is a little bit more detail of these molecules. And coming out of the cell is this long thread-like structure, which are called flagella. And these flagella, so in this movie that you saw of the moving bacteria, this spiral corkscrew-like structure, those are the flagella, right? And those flagella are turning, and that's what eventually causes this bacteria to move. And you also see here that there are many flagella, right? So there's a bundle of flagella. And that's what you're seeing here in this cartoon. And what is this flagellum is attached to this cell via something that looks like a machining, right? It looks almost very precisely machined, like what we would expect from a technological machine, right? And in the middle over here in this grayscale is an actual picture of this molecule that we have from electron microscopes. And you can see that it truly resembles a machine in some sense, right? So here are some other structures from within the cytoplasm of this biological cell. So you see here that there is a beautiful ordering, this hexagonal ordering of these molecules and these membranes, etc. inside the cell. What I want to point out to you over here is that just like in solids and liquids that we discussed earlier, there is also some very fine ordering in biological cells. Right? So in some ways, some of these structures can be thought of in the same way as we did materials, simple material. But just like the sand example that we talked about, all these molecules or bigger structures are coming together and then eventually forming this cell. And the coming together of these various things are eventually what will give rise to the properties of the cell itself. That is, that it can grow, it can divide, it can move, it can evolve, all of those things, which are the descriptors of biology itself, right? But to a first order, we can say that there is a very clear ordering and structure to biology, just like there is an ordering and structure in our everyday materials of solids, liquids, and gases. But I want to tell you also that not any ordering or any structure will give rise to something living. Here is a beautiful demonstration of this idea. This is from a book called Dynamics of Development by Paul Weiss. And it's a rather gruesome example, excuse me for that, but it makes a beautiful point. In the leftmost image is the embryo of a chicken. So what Paul Weiss did was and you will recognize this because it has a particular order. it has a particular structure, it has a particular shape, and so on, right? And as we also just discussed, this structure and shape is ultimately, of course, comprised of atoms and molecules. So what Paul Weiss has done to demonstrate this point, he's taken this embryo and he has crushed it, taken it, put it in a mixie and blended it. That's the middle image, right? So in some ways, we have removed all the structure and all the ordering that exists for this chicken embryo. So you might say that, of course this has died, that this is not living anymore. You might say that because it has lost this ordering, it has died. But in the last image, he does something else. He takes this soup of material and puts it in a centrifuge. So what a centrifuge does is that it will take the heaviest of these molecules, put it to the bottom, and the lightest ones will be on top, right? So here is a gradient of this material. It's ordered. There is a particular order to it. The order being that the heaviest, the biggest molecules are all at the bottom, the lightest ones are on top. So you might say the middle picture has complete disorder, the left picture has some order, the right picture also has some order. But we will, again, not call this order as living. Whereas this order, which is on the leftmost, is living clearly. So it's not sufficient that there is any order for these molecules. There's a very specific order for it to be living, right? Clearly, even this ordered soup on the rightmost side will not be able to perform the functions that a chicken is able to perform, right? Therefore, this ordering and structure in biology is not just in space, but it's also in time. If I go back to this picture that I drew over here, unlike for the sand, which only had spatial scales going from atoms to millimeters, etc., these things also have time, dynamics in time, right? So these molecules will be moving and their motions will be very, very fast. As human beings, let's say we perform functions and operations on the time scales of minutes and days and so on. And there are also some ecosystem time scales which are on time, years, hundreds and thousands of years, right? And all these movies must also already tell you that there is something moving, dynamic going on about all these biological functions. Therefore, to understand biology is to understand these interactions both in space as well as in time. Okay? And just like we are able to understand states of matter, what we are doing by doing research at the interface of physics and biology is asking, can we take the units, and these units in biology might be molecules, they might be cells, they might be tissues or organs, and they might be entire organisms themselves, right? Just like these could have been the atoms in the nitrogen or the molecules in water, etc. We are trying to ask, what if these were the cells in a biological unit? And there are some interactions between them, right? Just like the Leonard-Jones interaction, Leonard-Jones force, etc., or gravitational force, etc. There are some interactions between cells. What can they be? They're chemical signals that they're sending to each other. They can be mechanical forces that they're applying on each other, right? They can be coming because of some electrical signals that they're sharing with each other. As you already appreciate, these are much more complex than that simple gravitational interaction or gravitational potential. These are even more complicated interactions, right? And we have an understanding of some of them. But doing research at the interface of physics and biology means being able to ask the question, given a set of these kinds of interactions, and given these units, can we start thinking about the collections themselves and predict some or understand some properties of the connections, right? So if you remember in the slide I had told you about phases of matter, there was a diagram that we could construct over here which depended on temperature and this density. Temperature and density, in other words, are the forces or the interactions that these things are, that these materials are shooting. And we were able to construct a diagram irrespective of the constituent material, which all look the same, that below a certain temperature, below a certain density, it behaves like a liquid. Above it, it behaves like a solid. Right? The details did not matter. Therefore, can we do something similar for biology? There are, of course, many different atoms and molecules, but we don't know what these X and Y axes are because they're very complicated interactions. Can we construct a similar picture to understand where it will be living, where things will be non-living, etc.? That is one level of saying to understand biology. Right? Can we understand what these creatures are doing with respect to these interactions between these various humans? Okay, so I'm coming to the hour. I won't spend too much more time, but I want to tell you that these are the kinds of questions that occupy a lot of the research going on in many of our kinds of labs. If I were to tell you some of those details, that is, of course, another talk. But I hope I've at least so far been able to tell you what we mean by trying to probe biology in the terms or language of the way we understood other materials like solids, liquids, and gases, and so on. And I'm very happy to take more questions and go into more details of what these some of these research entails. And in the final few minutes, I want to tell you a little bit about the institute where I am, because it also gives you a sense for not only for the location, etc., but also for why such an effort is supported in such a center, right? Because it's called the National Center for Biological Sciences. It's in Bangalore, but it's an outcrop of the Tata Institute for Fundamental Research, which itself is located in Mumbai. And the TIFR in Mumbai does research in the various disciplines of science. One of them, of course, is biology. But as you will appreciate, all these different disciplines sitting in the same institute means that really there is no one discipline. And we are basically trying to understand this itself. And from this TIFR, this distinguished gentleman, Professor Ubaid Siddiqui, in 1991, came to Bangalore and founded this National Center for Biological Sciences. And Ubaid Siddiqui's view of biology was extremely wide. Right? And in the NCBS, National Center for Biological Science, he wanted to have research that spans going from the atomic and molecular scale all the way to organisms, to ecosystems, ecology and environment, to even the theoretical aspects of it, like the kinds of things that I explained to you. And within this NCBS, there are a few of us who have nucleated this so-called Simon Center for the Study of Living Machines. And this center brings together research groups who use theoretical and computational ideas to address complex biological problems at various scales, right? And this common philosophy that there is organization all the way from molecules to ecosystems, and there are these interactions which ultimately give rise to collectives which we view as living machines. That's the focus of this center. And with that, I'm going to thank all of you for your attention, and I'm very happy now to take any questions that you might have. Thank you.
Varun? Shail Mash. Okay, good. Thanks, Shail Mash. I am not competent to comment on this very simple thing, a complex thing made so simple to learn students. Two different subjects which affect the nature, which affect the science, which affect our understanding is so nicely put forward. And, something, it's a unique talk we had today. We never had this kind of an approach on scientific subjects such as, core subject like physics, biology and all that. So nicely done. And, knowledge and understanding hidden behind and between subjects. Something very, very, it opens up, widens the horizon of students, how they look at science, how they look at nature, how they look at what happens when a matter is subjected to a change. See, something very, very different, and I learned a great deal. I don't know how to thank Dr. Shashi for it. It just so happened that his father was in Calicut in the beginning of last month, in the middle of last month. So I wanted to meet him. I went and he's a great fan of Ramakrishna Mutt, and he was there earlier also, 2, 3, 4 years back also he came here. So I just went to meet him to pay my respects to him. And there, we incidentally talked about Shashi. And, then only I came to know that he moved to NCBS. So there the whole idea came that we should have a talk from Dr. Shashi. So thank you very much, Dr. Shashi, for enlightening in such a great way to our thing. And here in our talk today, I find Sahadevan, T.N. Sahadevan from London is listening, I think. He's in UK now. I saw him. I don't know, is he still continuing? I saw Pappan, our P. Pattanabhan. Also, I saw Pappan. Are you there? I saw Dr. Ajit. Great veteran people, who are whom we look forward.
Okay. Yeah.
Oh, whom we look forward for guidance for our student. It is so nice and wonderful day for us. So thank you very much, Dr. Shashi. Please go ahead. Students are waiting to ask questions.
Can I ask a question? Okay. My name is Archit. I am from Kozhikode, and I am studying in 7th standard, and I am studying in Ayathan school.
Okay.
And my question is, recently the James Webb Telescope captured planets' chemicals. So it found that there is a presence of water in the planet name is VASP 96. I think that VASP. So how the James Webb Telescope found there is a presence of the water in the planet WASP 96, because the distance between the Earth and the WASP 96 is the distance in light years. So how they found it? That's my question. That's my question.
Sure. That's a very interesting question because it requires a lot of technological advance to be able to do something like that. Right? So what they are really looking for are what are called spectral signatures of water. Right? What does it mean to have a spectral signature, first of all? So as I told you in my talk, there are all these various atoms that eventually comprise material, right? So even for water, there is hydrogen and oxygen and so on. When these molecules come together to form water, depending on and to excite, so the collective property of this water will
Hello, my dear boy. I didn't get your name. Can you just tell me your name?
My name is Archit.
Archit. Did you ask a question in the 2 months back July program?
Can you tell again? I didn't hear.
You are in 7th standard, isn't it? 7th standard, isn't it?
Yes, I am in 7th standard. Yes.
From your same school, another boy had come, and I am not able to get back his name. Ayathan school, isn't it? Ayathan.
I'm studying in Ayathan school. Yes.
Okay. Good. Okay. It's good. We would like to continue with your type of boys. That's why students. Okay. Thank you.
Sorry.
Let us proceed.
I lost my connection.
Shashi is back.
Yeah, sorry, I lost my connection for a second. Yeah. So what I was trying to say was the presence of water on one of these planets will mean that, so the detection of this planet itself is done through what is called a spectral means, right? That you're detecting the radiation that is emitted by this planet. And in that spectral signature, there is this spectral signature for water itself. Okay? And what does that spectral signature mean? It means that ultimately the coming together of hydrogen and oxygen in this certain way will give rise to a vibrational spectrum of that molecule, right? And that is what one is looking for, and that is one detects when one says, "Oh, there's water here or water there."
Okay, so that method is used for identifying the matters and molecules in the other planets,
exactly.
Right?
So, exactly, yeah. Or even probing matter and material even on Earth itself, right? To probe the spectral properties. This is what's called spectroscopy, right? And so you extend that same principle out into outer space, and then you're able to say what is the components or the composition of planets and stars and so on.
Okay, sir. Thank you. Thank you for clearing the doubt.
So I'm Yutika. I'm in year 9 and I'm in Global English School from Calicut. And I just have this little doubt, as you were talking about really minute particles. this stuck up in my head about string theory, especially there was a madly going topic in 2016 World Science Festival that insert all these protons, and there are little strings which vibrate, and they are the causes of creation. So could you just elaborate on that topic? I have a lot of spacing dubs in that.
Right. I myself don't know anything about string theory, except that it is an effort to try and describe the organization of higher levels, which are of subatomic particles and so on the basis of an underlying structure. But beyond that, I myself don't know too much about the details of it, and I don't want to give you the wrong impression of what it is.
Yes, sir. So do you go with that theory? It's widely accepted, and it's also not accepted by many other scientists.
So you see, in science, one of the crucial aspects is that a theory is only right or wrong until it's wrong, right? And all theories eventually reach that stage because you discover more and more about the universe, about you, right? Therefore, only time will tell if some of the predictions of string theory turn out to be valid and so on. And that will ultimately depend both on experimental tests and how well the theory itself is able to capture aspects of the natural world.
Thank you, sir. So I also had another doubt. Is dark matter actually a sort of matter?
Yeah, it is.
What kind of matter is?
Sorry?
What is the state of matter?
What is the state of matter? Is it? You're asking if it's solid, liquid, or gas, etc., etc. Right?
Yeah, I've actually read there are 20
in that sense.
Yeah.
Yeah. In that sense, we have absolutely no idea because we have no tools to probe this kind of matter, nor do we have any way to understand its organization. And you might also appreciate that even solids, liquids, and gases are not the only states of matter. So there can be other exotic things that can happen, and that is already with the matter that we know and observe. And therefore, this dark matter, which is there are no direct probes of it. We have really no idea of in any deep way its organization.
Yeah, thank you, sir.
Sir, one more addition here.
I have another.
Okay. One more addition is there. Our students are with great. Archit, please be there. Then one more suggestion, one more comment on this lecture we have to make that the students are asking very, very serious and heavy questions. But actually, nowadays, as a teacher, I could see that students are not looking to the nearby objects with their mere observations. They think that the things exist in the huge things, but the things are readily available with their near places and with near to their eyes. One more suggestion: to open their eyes and see the things very close to them and analyze them, then can proceed. Okay, then you can proceed. Archit,
yes, Archit, go ahead, Archit.
Okay. I have a small question that what's the difference between dark matter and dark energy? Because dark energy has most of the space in the universe. I saw that 25% is something dark matter and 5% normal matter, and remaining is dark energy. What's that? Dark energy and dark matter. What's the difference between dark energy and dark matter?
Well, at a fundamental level, energy and matter are interconvertible, right? And therefore, it might be one and the same way of saying about the same thing. It might be two different ways of saying about the same thing. But, the very fact that we call it dark means that we don't know very much about it. Right? So there are, and again, I'm no expert. I'm really no expert in all of that.
I don't want to.
Good evening. My name is Abhinav. I'm an undergraduate mathematics student. So in the starting, we were discussing about the hierarchy in sciences. So I agree that there is no hierarchy in sciences. Even though there is no hierarchy, we have to, for example, we have to unify the laws of nature. Fundamentally, to understand the laws of the nature, we have to go either to the fundamental level of physics or to deeper mathematics. So, thing makes more fundamental are these theoretical physics and mathematics can be denied in that sense.
Right. So, yeah, maybe I'll try to make the point again. Right. I don't think that there is anything. I mean, I don't think any one thing is more fundamental than any other thing. So mathematics might be the language in which or through which we describe nature around us, right? But that doesn't mean that if we understand mathematics, we will understand the universe. To give you a small example, that is why I tried to bring up this example of the sand, really, right? So we do understand how atoms will come together to form the crystals in a sand grain. We do understand that. But to be able to say that the sand as a whole flows, we will never be able to predict that from the atomic level alone. Right? That is really and let's say we take the example of water. Water flows. It has something called a viscosity. It has something called a surface tension. There is no way for us to predict a viscosity or a surface tension from an atomic theory. Okay. There are what are these called? These are what are called as emergent properties, and these emergent properties are what make every level of organization just as fundamental as every other level of organization, right? And therefore, this notion of saying we will understand the most basic particles and from that we can describe everything else is wrong, I think, or at least it's incomplete for sure.
Chair.
No?
Sir, but
Yes, sir. Is there any other question?
Yeah, Abhinand, please go ahead. I don't think I've convinced you.
My question is that even still, we can predict these emergent phenomena as a statistical property of this matter. To a degree, we can predict that, except there is no turbulence.
No, unfortunately not, right? So if I were to ask what is the viscosity of a single atom of a single molecule of water, that question itself is meaningless, right?
In the macro scale, predict in a statistical way that.
And no, so there is, so we don't have any theory right now which can predict this property of viscosity even coming up when you put a bunch of these things, a bunch of these molecules together, right? And also, let's say you want to describe the flow through a river, you will not describe it in terms of the molecular interactions. You will describe it in some other higher level of organization, fluid parcels and so on, right? Therefore, you might be able to reach a certain level of description from a lower level, but I don't think you can go higher than that and predict more emergent behaviors. Right. See, for example, it's the same molecules of carbon and iron and phosphor and whatever else, which is, let's say, in a grain of sand. But it's the same material in a cell. But one is living, the other is not living. One can grow and divide, the other cannot, and so on, right? So you cannot predict all of these things from a lower level of
students, is there any other questions from your part?
Good evening, sir. Sir, my name is Fatima P. Anwar. I am a PG student, but I don't know much about the biophysics area. But I was asking whether the gravity has, I already typed it in the message box, gravity have an influence on the growth of living organism. If there is such a thing in the outer space, is there a possibility that gravity influences the growth of living organism?
Yeah, I certainly think it does, and we have a lot of evidence to show that gravity affects the functioning and even the growth and organization of living systems. Right, plants are a classic example. They use gravitational cues for their growth and so on. Simple things like density differences, etc., make a huge impact on the functioning of biological systems, and all of that is eventually dictated by gravity.
So, sir.
So the answer is yes. Gravity affects biology.
So, sir, when we are actually checking on to Mars missions and all, we are actually looking forward to see whether there is living organisms existing, right? So we need to check the conditions relating to gravity also, right?
Absolutely. There's no doubt about that.
Sir?
Yes.
My name is Lakshmi. I am a 9th standard student in St. Joseph GSS Alapura. I don't know my question is genuine, but I have a doubt. In physics, we said that substances are made from atom, then molecule, compound, substance. But in biology, we said that atoms, then molecules, cell organelles, cells, tissue, organ. And is it so? And if so, what's made this difference?
It is so. It is so that these organizations are different in what we call living and non-living, or physical and non-physical materials, or biological materials. What makes it different? It's ultimately the structures, the higher order structures into which they organize. Right. For example, in a biological cell, or let's say a biological molecule, the same atom of carbon and nitrogen and phosphor will form a different shape and organization than it will in a crystal like glass, right? And it is that way in which it arranges itself that leads to a higher order interaction between these molecules and so on. And it's that higher order interaction which then affects a higher order function, an emergent property and so on, right? And that is what eventually will separate what we will call the living versus the non-living. It's the way in which these things are organized. I hope that answers your question.
Yes, sir. Thank you.
Other questions?
Are there any more questions?
Any more questions? Navneet,
can I ask a question? A small question. Can I ask a question?
Yes, please.
We have all humans and all objects have a weight. According to the gravity, the weight is changed. Right? If there is, if I am 40 kgs in the moon, the kg will be different.
Why?
Right?
Why is that? Why is that?
Because the gravity changes. When the gravity changes, the pull. When the gravity changes, the pressure will be low. So the weight will be decreased.
The force. Yeah.
Yes. So, how to find an actual weight of a human? Is there any actual weight of human, or there's no actual weight of human?
Yeah, there is no actual weight, right? So if you remember, in this slide I had showed you about this gravitational interaction between two objects, right? So what you're calling the weight is this force with which one object pulls another. So let's say this M1 is the Earth and this M2 is us. The force with which this mass is pulling us is the weight, correct? And there is a constant over here, G. And this G is different for Earth, it's different for Moon, and so on and so forth. No, sorry, what am I saying? Little g is different. Big G is the same, this M is different.
Okay.
Right? Because this M1 is different, you will experience a different force, whether you're on Moon or Earth or so on and so forth. So there is no real weight, correct? It all depends on the combination of this big G, which is a constant, and this M1, which is the mass of that planet wherever you are. So the weight that you feel, which is the force on M2, will always depend on this combination. There's nothing, there's no true weight.
There is no actual weight of an object, right?
The actual weight is, there is no, it's only when you have another mass that you have a weight, first of all.
Okay.
If you're floating around in vacuum, there is no mass. There's no force.
Oops. Thank you.
Can I have a question?
Yes, please.
If all students have questions are over.
Yes, Papan, go ahead. Go ahead.
No, you check out whether any student wants to raise.
No, they will follow.
I am an old man.
You go. Please go ahead, Papan. Please go ahead.
Professor Shashi, thank you for the very interesting lecture.
Sir, wait, I have a doubt.
Thank you.
Oh, please.
Sir, most of the natural processes are irreversible. By considering a rock, how initially this powders of the rock are together to form a rock?
Sorry, you're saying most processes are irreversible. Yes.
By
Yes.
considering a rock,
Yeah.
by considering a rock, how the powders of the rock, how it going to build together to form a rock initially?
Sorry, I didn't fully understand. You're asking how many different grains of sand or rock come together and give rise to a bigger structure? Is that the question?
Yes, how?
Yeah.
We are
Okay.
crushing a rock, but we can't together it to form its initial stage as a rock. By
Okay, so
crushing a
let
rock,
me
we
try
get
and
powders, and those powders can be after
Reassembled
we
is what
can't
you're
create the rock.
I understand what you're saying now. You're asking if I take a rock and crush it, it becomes powder, but it's not easy to go back in the other direction. Correct?
Yes.
That is the question. That's the question. It turns out that with a rock, you actually can go back because, I can crush the rock, it becomes powder. But if I melt the powder and then if I let it to crystallize, it will go back to the rock, right? So in that sense, that process is indeed reversible. It may not form the exact same rock because the exact same rock will, meaning, it's formed through some historical process, right? It will have aged in a certain way, it will have come together in a certain way, and so on and so forth. So that's a good point. But if you were thinking about, instead of rock, this embryo which is living, and then I crush that, right? There is no way for us to go back in this direction. So in that sense, this is very irreversible. The only way we know how to take this crushed material and take it to another chicken is to feed an intact chicken with that material, and then you will get another one because it gives birth to another chicken, right? but we don't know in any fundamental sense to take it back in the reverse direction. But with the rock, we actually know how to do that. Does that answer your question? See, for example, salt, if you take salt, I can take a salt crystal, and if I mix it in water, it will become sodium and calcium, right? But I can recover that crystal from that water. But you know that if I dry off the entire water, salt will form crystals again. You can try this experiment at home, right? You can mix salt into water, it will go away. And then you evaporate all the water, you will get back the salt crystals. So it is a reversible process. You're confused.
Who is this Misna Fatima?
Misna, did I answer your question? Or?
Misna is a question, I think.
Misna, did I answer your question or did I confuse you more?
No.
Okay, Pappan, please go ahead.
Professor Shashi.
Uncle, yes.
I am Padmanabhan. I am retired ISR engineer. I don't know much of biology.
Yes, he has addressed already you as uncle.
Thank you. Okay, so he doesn't want me to ask much questions.
No, not like that.
Professor Shashi, my daughter is working on microbiology and molecular genetics, and she did 1 month course in your TIFR in Bangalore, and she is very much proud about mentioning that in your. She would be very happy to view your video. She's now in the United States. She would have been able to do that. I will ask her to see that. She told me in 2012, when she was doing her research as a research assistant in Yale University, one mathematical professor gave a lecture with a video which he generated mathematically, the stage of development of an embryo into a child, or the 9 months growth from the embryo into the child and the birth process of that. I don't know how much of the mathematics, how much of physics, what theory he has used, but I remember that statement she made to me when I was listening to you. I will ask her to see your presentation. Now, I have one question. The physical world and the biological world. As per biological world also is the same collection of atoms. And physical world also is the same collection of atoms. Now you say that the structure of atoms only distinguishes between the two worlds. Are we very near to the condition of generating life in a laboratory from non-living atoms?
That's a very deep and nice question. And so it's not in the structure of the atom, it's in the collection of these molecules, etc. Point number one. But it's atomically, they're all the same. But they're nowhere near being able to recreate life in the laboratory, I would say, because what we are missing is, even though we might understand the constituents, we have no idea about the interactions, right? So the picture that I showed over here in this sort of abstract sense, that there are these molecules, and it is the interactions between these molecules that will eventually govern how the entire collection of molecules is going to behave. Right? We have no idea about what are the right interactions. We have no idea about how many of these units to put in. We have no idea about the boundary conditions in which we have to put in these things, right? And all of that, see, for example, if I were to say in terms of information, and and as you said, if the information of a living system is in its constituent material, we have all the information, and it's actually not much, right? Because it's simply taking stock of how many molecules of what there are, or how many atoms of what there are. But most of the information in building an organism is actually hidden within these interactions of boundary conditions. And we have no idea about that. And therefore, I think we are very, very far away from being able to reconstruct life in the laboratory from scratch. Although there are some efforts ongoing, I would say.
Thank you. Good, sir. My question is over.
Oh. Navneet, are you there?
Yes, sir.
Varun?
Yes, sir.
Navneet, go ahead. Any more questions, Navneet?
I think it's all over, sir.
All over. Who is giving to Abhinand? You want to ask something?
Yes. That's related to Pankaj sir's question. That is, even though we can't make this consciousness and all, we are trying to make the synthetic meat and all. So, how that will eventually be making life?
Right. So when we say synthetic meat, it is, it's not living in a very deep sense, right? Even though they might be comprised of cells, it's a bunch of cells that are growing into the form of a blob that we eat. And we will call it living only when that entire thing is able to grow and reproduce on its own. And that is an ability that we have not yet been able to achieve in the laboratory.
Okay, Abhinand. I think, Navneet, if no more questions are there, you can close and say a vote of thanks.
So, someone
There
just
seems
raised
to be one more question.
I guess there's one more question.
Sir. So my name is Abhishek, and I have completed my class 12 last year. So I have trouble in understanding the basics of physics, but I understand biology in a better way. But my question is, it's a basic question. What actually is energy? Because some say it is the ability to do work, whereas energy is also visible when it comes to humans. We are also able to do work. So there is a different definition of energy there. So actually, what is energy? And also in other books, for example, in sci-fi, like Dan Brown's book, they are mentioning about pure energy. So what is energy? That is my basic question.
It is the ability to do work from the physics definition, right? And what is work? Work is the action of a force on an object. That is the fact that a force can displace an object in a certain day, right? And energy in science is defined this way and this way alone.
Sir, so can you please?
And that force can be gravity or what have you, right? But it's the ability, or rather, it's it's the action of this force on an object that results in a quantity called work. That is what we call energy. It's a matter of definition.
Okay, so can you give a different perspective of energy, or is it defined as energy? So we are abiding by the definition that this is energy, and can we say that energy is something? Can we visualize energy as something?
What we are visualizing is the consequence of the transformation of that energy, right? In any process, whether it be the heating of a vessel of water or something like that. What we are watching there is the transfer of energy from one form to another.
Okay, thank you.
Shashi, this creates another question. We do not know what creates gravitation. We do not know what creates magnetism. We know electricity is flow of electrons, leave it. We don't know what is we don't know what is magnetism, how they are created. Now, can I ask that?
We
or
do
can I
in
ask
terms of
that life is something like a third form of energy, which we cannot see. We cannot feel it like magnetism or like gravity.
Hello?
Right.
Hello?
Sir.
Hello? I think I lost that question midway.
Okay. Can I repeat that?
Yes, please. Yes, please. Yes, please.
Yeah, sorry, Kuti sir, can you hear me? Shajal sir.
Yes.
I can hear you.
Okay. Professor Shashi, see, we know Newton's law, which says gravity between two masses. Masses are absolute. We know magnetism. We don't know what is magnetism. We don't know what is gravity, how it is generated. Entire universe is controlled by gravity. Now, can I say that life is another form of energy which we are unable to feel it or mathematically measure it? It's just a unit except seeing it by our world.
Right. I mean, ultimately, I think so. What I'm trying to imagine, what I'm trying to convey here is that the living state comes because of the interactions between various molecules, and underlying that ultimately is a chemical form of energy, right? Because that's the basis for it, the food we eat, or for plants, it could be from sunlight and so on. So that is the only source of energy that animates any living creature, either chemical or this light energy, right? And it's the transduction of that into various other forms that give rise to the functioning of living systems. And that's how I would put it.
What next, Navneet?
So I think all the questions are over right now.
Okay. Then you can proceed.
Sure, sir. So good afternoon, one and all. My name is Navneet, and I'm a 12th standard student and a member of UL Space Club. So today, first of all, I would like to extend the sincere gratitude on behalf of UL Space Club to Dr. Shahi Thutupalli for giving us this wonderful session. And this session has been a really wonderful thing, since the way I put it is like today's session was more about the things that we know and yet we don't know. Well, the reason why I'm saying is that, well, all this time, especially as school students, have been led to believe that almost everything that we see is actually exactly classified into different subjects. And while we are studying a single discipline, we have to follow it entirely. But as we grow up, we are actually seeing the bigger truth that almost each and every single thing that we see in our day-to-day life, or that the things that we hear in our day-to-day life, is like entirely interdisciplinary. So the time is long gone when we could actually literally classify the things into different sections. And also today's session has been also gave us an insight on the fact that most of the things that is actually present all around us has a lot of interesting science in it. And by science, I mean interdisciplinary science. We can connect and build up on the current existing things, and we can build our own things, and we can actually understand the world around us in a much better way. Also, I guess that I felt so that there was a meaning that I found in today's session, and I'm going to share it with you guys. Now, the thing is that in the famous book Alice in Wonderland, Lewis Carroll once actually gave us a hidden message. Well, it was like that when entirely unrelated things are connected, we get what is called creativity. And in today's session, we actually saw that. We saw that we could connect different disciplines like biology and physics, which are entirely different, and we could get something even more beautiful, which would help us to understand the world around us in a much better way. And in each and every aspect, today's session was a wonderful session. So once again, I'm thanking Dr. Shahi Thutupalli on behalf of all the UL Space Club members and all the people present here. And also, I would like to extend sincere gratitude towards our dear Ike Kuti sir, Padmanabhan sir, and all of the UL Space Club coordinators and members. And also, the most important, all the participants who are present with us today. So thank you one and all, and have a nice day.
Thank you, Navneet. Thank you, Navneet.
Thank you so much.
It has been a wonderful evening for us, wonderful afternoon for us. Very
Thank
nice.
you so much.
Very nice. Okay.
Thank you.
Akshit, is Akshit here still? Is Akshit here? I think he left. I think this boy appears to be too good. He's in 7th class. I had to find out where is he and all that. We had to catch hold of him. Varun, are you there? Okay, so we had a wonderful afternoon, and it's so nice of you, Dr. Shashi, to have come and spend a good amount of time, almost 2 hours with us. It is an excellent gesture on your part, and I think we will continue with the association in whatever manner you think appropriate.
It's a pleasure for me, Uncle. Thank you for having me. Yes. Upon Uncle, it's so nice to see you.
So is the case with us.
I am in Bangalore. I'm a very good friend of Sahadevan. I don't know whether you know Sahadevan.
I know him.
Papan, he is TGK Murthy's son. Papan, don't you know Dr. Shashi is TGK Murthy's son?
Oh, Shashi.
Your son will know him.
I know him.
He knows me. He knows me.
Shashi, I'm sorry, Shashi. Because I thought he's from Malayalam, Kerala. And,
no.
I'm sorry, Shashi.
Until now, I thought you recognized him, you know him. I never knew you never recognized him. You couldn't recognize him.
I couldn't recognize him, but there was some semblance. But sorry, Shashi, I am very, very sorry.
No, it's fine.
But when you say Shashi Thutupalli, I think you are from somewhere from Kutti's area, Talasheri or somewhere. I'm sorry. It was very nice to hear you, Shashi. And my daughter, you know Meenu. Meenu will be very, very happy to listen.
Yeah, he knows. Actually, Meenu, Papan's daughter Meenu gave a talk in this webinar in last April.
Okay.
How is your dad?
Yeah, doing fine.
Oh, thank you, Shashi. I'm very sorry. Please.
Papan, I don't meet him in Bangalore, but I met him in Calicut. TGK.
What?
TGK.
Oh, he's there now, TGK in Calicut?
He was here about 2 weeks back.
About that?
Oh, wow. He doesn't take rest, I hope. He cannot. Oh, wow. I'm very sorry, Shashi, that I couldn't recognize you.